Okay, so this is Form A from yesterday's quiz. I'm just going to go through this in order, and if you have questions as we're going through, you can ask. Number one was a problem that only about 55% of people got right, so it is one of the questions that was missed somewhat heavily. So again, as I said, listen up, and if you need to take notes as we go over it, please do that. Number one says, a baseball collides with a watermelon at rest. During the collision, how does the impulse on the baseball compare to the impulse on the watermelon? And we talked about this in our notes. Okay, I told you that any time we have two objects that collide, we've talked about this for a couple units, at least related to this. Anytime you have a collision between two objects, whether it's a bug and a car, or a semi-truck and a car, I think those were the examples you've seen in there quite a few times, the forces are equal and opposite. It's a force pair, right? So the force on the bug is equal to the force on the car, or in this case, the force on the baseball equals the force on the watermelon. It's impossible for them to be touching each other for different amounts of time. If they're in contact, they're in contact with each other, which means that the time of the collision is the same, and the force of the collision is the same, which means that the impulse is the same. If you have two objects collide with each other, it doesn't matter if one of them is bigger than the other one or anything else, the impulse will be equal in magnitude because you have the same force and the same time, and impulse is force times time. So the force times time of the baseball equals the force times time of the watermelon, and so the answer to this is C. The impulses are equal in magnitude, and this will be any collision, not just a baseball and a watermelon, anything. Okay, it doesn't matter what it is. If you have two objects that hit each other, they have to hit each other. If it gives you like car A hits a wall and then car B hits a different wall, not the same thing. If they hit each other, then this will be true. Okay, so again, the answer to number one should have been C, and as I said, 55% of you guys got this right, but that does mean 45% of you missed it, so if that's you, then please make a note. Question 2, though, you did much better on. Question 2 is pretty straightforward. Which of the following has the greatest momentum? 93% of people got this right. I'm not sure the 7% that missed it, but all you have to do in this question is remember the momentum equation. Momentum is mass times velocity, and that's all you're doing. You're taking the mass and the velocity in each of these statements, multiplying them and getting the momentum, and it's a different number for A, B, C, and D, and then you're just comparing them and picking which one is greatest. Okay, so you're looking for greatest momentum. If you look at these values that you have in here, let's just go ahead and multiply each one out. I've got my calculator right here. So for A, that's going to be 1540 times 38. For B, it's going to be 1210 times 51. Okay, so far, B is already greater than A, so I can cross off A. Okay, now we're comparing B to C. C is 6120 times 10. Okay, those two are similar, 61,710 versus 61,200, but C is less. Okay, and then D is 2250 times 25, which is still less. So the one that was the greatest was B, and again, that's all you had to do was go through and solve each one. But this value here we had for the second one was the greatest of the four, 61,710 kilogram meters per second. All right, number 3. Number 3 was one that you guys struggled with. This may be the most missed question. It is. Okay, only 40% of you got it right, which means more than half of you missed it. Okay, campus-wide, that's not just your class data, that's the whole campus. It says, which could show an object experiencing a negative impulse. So, just as a reminder, impulse is force times time. If you have a negative impulse, it means you have a negative force. You can't have negative time, right? Okay, so that's all it's asking is which one of these diagrams shows something with a negative force. Okay, if we take a look, this one right here absolutely has a negative net force. So this looks good. Okay, there is a choice that says all of these, so we need to look at the rest of them. Okay, if we look at answer choice B, Although this graph has a negative slope, this is an XT graph. This is a position time graph. A negative slope on a position time graph just tells me I'm going backwards. That's it. If the slope changes and I have a curve, then we have acceleration. I don't have that. I have here constant speed. Constant backward speed, but constant speed. And if I have constant speed, that means I have a net force of 0. Okay, so that can't be a negative impulse because it's not an impulse at all. There's no force here. There's no net force, constant speed. Let's just talk about C. We already know it can't be D because it's not B. C shows an object that is moving forward. It tells us to read it from left to right. And it's moving forward and it's speeding up. And that means that it has to have a positive net force, or its net force has to be in the same direction as its motion because it's getting faster. Okay, and so this one would be a positive net force, not a negative one. That would be a positive impulse, not a negative one. So the answer you should have selected for number 3 was A. That is the only one that would represent a negative force and thus a negative impulse. The most common wrong answer was D, so a lot of you thought that it was all of them. Okay, it's not. It's just answer choice A. All right. Make sense?
Yeah.
Number 4. All right, number 4 has a force time graph. We've seen force time graphs in our lab. We saw force time graphs in our problem set. Okay, we know, or you should know, that the impulse on a force time graph is the area. Okay, before I even look at this, if I see a force time graph, I should immediately be thinking that impulse is force times time, and if you multiply your x and y axes, that's the area. Okay, so the area of this graph is impulse, and that is going to come in handy when we read the question. Hold on, let me read the question first. It says, the graph below shows the net force acting on a bowling ball as it rolls down a hallway for 8 seconds. Determine the impulse from 2 seconds to 8 seconds. So that's one issue. If you didn't read that carefully, you are not finding the entire area. You are only finding the area from 2 seconds to 8 seconds. You want this portion. That's it, because that's what the question says. It says it right here, 2 seconds to 8 seconds. So make sure you're reading it because it's not always the whole area. Okay, so that's all you're going to do. You're going to find the area of this. Now I'm going to break it into regular shapes. I have a rectangle right here, and then I have a triangle over there. Okay, the formula for the area of a rectangle is just length times width. We're going to use the numbering on our axes. The length of this, if we're reading across this way, this goes from 2 to 5, which makes the length 3. Okay, and then the width, if we go up, we can use the numbering on the axes over here. It says a 3 by 2. Okay, so the area of the rectangular portion is 3 times 2, which is 6. The area of the triangle, again, the formula for area of a triangle is 1/2 base times height. The base of this triangle goes from 5 to 8. That's a base of 3. So this dimension is 3. So 1/2, 3, times the height of the triangle is 2. Okay, so that's half of 6, which is 3. And so we want to do 6 plus 3. That's my two areas. And we get 9, which is answer choice D for number 4. There wasn't even a choice to include this because there's not a bigger one, so I guess that wouldn't be where you messed it up. But that is how you do this. Just find the area of the time that's described by the question. Sometimes it's not the whole time, okay, so please read those questions carefully. But if you see a force time graph on your test tomorrow, find the area and that will give you the impulse. And maybe you can use that impulse to calculate something if that's what you're being asked to do. Or maybe the question is, what is the impulse? Or what is the change in momentum? Same thing. Okay, and then you're just going to find the area. All right, so again, number 4 should be D. And 60% of you got number 4 right.
So wait, if you go, so you did 3 times.
I just found the area.
Okay, so.
All right. You can look, if you want to look at additional examples, go into the problem sets or go back to your notes because we're not going to talk about how to find area
Quick
right
question,
now.
ma'am. Did you just do the did you just do the time? Did you just take one from the rectangle and one from the triangle?
Yes.
Got it.
All right. Number 5. We got to keep moving. Number 5 says a 65 kilogram cannon launches a 150 gram cannonball horizontally at a speed of 32 meters per second. With what velocity does the cannon move? First things first, before I get into this at all, I want to point out that this says grams. Okay, if you read the question and you see grams, you need to have red flags going off in your head that say, I need to do a unit conversion, because you do. Okay, so let me move this up so I can have more space to work. All right, so I already know that's going to be a problem. It's focusing. All right, we're looking for the velocity that the cannon moves. So we have a scenario here with a cannon and a cannonball, and they're going to end up moving in opposite directions after this explosion that happens between the two. Okay, we've looked at examples like this before. I know that again, in any collision or explosion, this is going to count the same way. I know that the impulses are going to be equal in magnitude. Okay, so I know that the amount of impulse here equals the amount of impulse there. And I know the information for the cannonball, because I know both its mass and its change in velocity. Okay, and so that's what we're going to use. We're going to use the mass and the change in velocity for the cannonball to figure out the cannon's velocity. Okay, because again, anytime you have, whether it's a collision or an explosion, there's my explosion between the two. Okay, you're going to have equal impulses. And impulse is equal to force times time, but that's less useful here. Impulse is also equal to change in momentum, which means the mass times change in velocity, and again, absolute value, okay? The mass times change in velocity of one of them equals the mass times change in velocity of the other. They're equal in magnitude. Now, I do want to put signs on this. I'm going to call this one negative, okay? So whenever I do this, I'm going to say negative m delta v equals m delta v. Okay, because they're equal in magnitude, but they are opposite in direction. So one of them is negative. You need to make sure that you indicate that. Okay, so with all that in mind, let's go ahead and take a look. And actually, we probably don't need the negative because it's in the question, but I just wanted to point that out. Okay, so we're going to say that the cannon is this one here on this side, and this is going to be the cannonball. All right, so my cannon, I'm going to have my 65 kilograms, and my cannon has a change in velocity, but I don't know what it is. That's what we're trying to find. Okay, my cannonball, on the other hand, has a mass of 150 grams, which is 0.15 kilograms. Again, you need to convert it by dividing by 1,000. And then it has a change in velocity of 32 because it starts out at rest before it's fired. So its change would be 32 minus 0, which is 32. I'll write the minus 0 just so you don't get confused, but that's my delta V. All right, so we're going to do 0.15 times 32, and I already have my sign taken into account here. So when I solve this, I'm going to need to add a negative on it because it's going to end up giving me a positive value, I think. But let's look. 0.15 times 32 gives me 4.8, and it's equal to 65 times delta V. Again, we're going to divide both sides by 65. And so 4.8 divided by 65 gives me a change in velocity of 0.074. It's actually 0.0738. Okay, that's my change in velocity. But notice this one was a positive change. This one needs to be a negative change. It's not going to give me the negative sign. That's why I said they're equal in magnitude.
I can't see the bottom.
Okay, so you need to remember to tack that negative back on. Okay, or just look at your picture if you drew one. It's going to the left. Put a negative on it. Draw a picture so you don't miss the sign. Okay, so the answer that you should have is B for number 5. And most of you got that. The most common wrong answer was A, which means you got the right magnitude, but you forgot to take into account which way it was going. Okay?
Like, how do you know which way it was being?
You draw a picture.
Draw a picture.
Draw a
But
picture.
how did you know?
Draw a picture. I already drew the picture. All right? All right, so again, when you fire something, one of them is going to go forward, one of them is going to go backwards. So they have to have opposite signs. Okay, number 6. Number 6 says, a freight train rolls along a track with considerable momentum. Suppose a similar train rolls at the same speed, but with twice the mass. The second train's momentum would be. This is just a proportional reasoning question. You know, or you should know, the equation for momentum is mass times velocity. And so this question is simply asking us, hey, if you have something that has 2 times the mass, how does that affect the momentum? And we did this. We looked at this at the beginning of the unit when we looked at the effect of mass on momentum when we did those marbles going down the ramp. We've seen it in our problem sets, and you can see it algebraically right here. If you double the mass and keep the velocity the same, you will be doubling the momentum. It is a directly proportional relationship. And so the answer to number 6 should be E, double. And almost everybody got that right. 94% of people got that one right.
I'm pretty sure I was one of the 94%.
All right. Number 7. Number 7 says, the reason padded dashboards are used in cars is that they blank. Padded dashboards aren't the best example of this, but airbags, better example. They do the same thing though. Okay, anything that has padding in it, whether it's an airbag, whether it's a padded dashboard, whether it's a football helmet, which is actually in the next question, anything that has that padding in it is going to allow that object to keep moving forward. It's going to increase the time of the collision, just like your bumper did. Okay, you put some soft stuff in there, some crumply stuff in there, because it allowed it to keep moving forward, and that made the collision take longer. And when you increase the time of the collision, you decrease the force. So the reason that they use padded dashboards, the reason that they have airbags, the reason that they have gymnastics mats or the padding inside of football helmets is that they increase the time of the impact of a collision. And when you increase the time, you decrease the force. It's the same thing that that you guys did in your infographic as well. So the answer to number 7 should be C. And I was actually surprised because we had done so much with this. I thought this would be higher, but 75% of people got that right. That's not terrible, but it should be higher than 75% when you guys just did an infographic on it. Hopefully you got that right in your infographic.
Has increased
the time. It's going to decrease the force.
Increase.
All right. Number 8. Number 8 is similar. Okay, it's still looking at the same type of relationship. And you guys did better on number 8 than on number 7. I don't know if it's the wording or because it's specifically talking about force here. But it says, in 1949, the NFL adopted plastic football helmets with foam padding inside. Prior to this, that's a typo, prior to this, players wore thin, unpadded leather helmets. If 2 players of equal mass wearing these 2 different helmet styles were involved in identical collisions, how does the force experienced by the players' heads compare? So they're not colliding with each other. Remember I said when you collide with each other, the forces are equal, but that's not this question. This question is asking you to compare 2 separate collisions, okay? So please don't tell me that they're equal. Instead, we're looking at how these helmets perform, just like if you compared your bumper to somebody else's bumper. Same idea. All right? And what you're going to find is the same relationship I just talked about. The padding that's inside of these modern football helmets increases the time of the collision. Your head can keep moving because it will compress the padding. And when you increase that time, you're going to decrease the force. So the force of the padded helmet is going to be less than the force of the person wearing the leather helmet, which for number 8 was answer choice A. It's actually written in the other order. The force of the person wearing the leather helmet is greater than the force of the person wearing the padded helmet. And again, it has to do with that impact time. Okay, it's going to take more time for this one to stop than this one. This one has less time to stop because it doesn't have the padding. All right. Like I said, number 8, 85% of you got it right. Number 9, though, was one that you guys struggled with. 55% of you got number 9 right, but that means, of course, that 45% got it wrong, so we're almost at half and half. And again, it's one that we should be getting right. It says 2 vehicles, a semi-truck and a small car, are traveling towards each other and then collide, bouncing off of each other. This is the same scenario that was in the review. Now, the question in the review had check boxes and you had to pick which statements were correct, but it's the exact same scenario. So you've seen it before. Okay, it says, which of the following statements is true regarding the change in momentum during the collision? Again, they're colliding with each other. Remember, change in momentum is the same thing as impulse. So this question could be asking what's true regarding the impulse. It'd be the exact same question. And the reason I mention that is because we have already talked about impulse in a collision. If 2 objects collide with each other, they have equal amounts of impulse, which means they have to also have equal changes in momentum. Okay, again, the impulses are equal because the forces are equal. It's a force pair. Okay, and the time's equal. So if you have equal impulse, you will also have equal change in momentum. And the one that says that is answer choice C. The semi-truck and car experience the same change in momentum. So number 9 should be answer choice C. And we've already talked about it in, I think, number 1. All right, number 10. Number 10 says, which of the following statements is true regarding the change in velocity? Now, we looked at this before as well. We said, hey, the forces are equal. Okay, that means that the mass times acceleration equals the mass times acceleration. When you have very different masses, you're going to have different accelerations. We also said that if you had equal impulses, you could do the same thing and have m delta v, m delta v. Okay, but the little mass will have a large acceleration, and thus the little mass will have a large change in velocity, whereas that larger mass will have a smaller acceleration or a smaller change in velocity.
So the car will have
okay, we haven't answered it yet. So whenever we're doing this, what's true regarding the change in velocity, the one with less mass is going to have a larger change in velocity, and of course the one with less mass is the car. So yes, the car would show a greater change in velocity. That's answer choice B for number 10. And even though you guys struggled with number 9, you got number 10 right. 82% of you anyway got number 10 right. Number 11 is also related to the same scenario. Number 11 says, assuming the time of the collision is the same, how would the force of the collision compare if the 2 vehicles were to stick together and stop instead of bouncing apart? We looked at this in our notes as well. We talked about how if you go play paintball or if you've had a water balloon fight, we talked about how it hurts more if it bounces off as opposed to if it sticks to you, if it bursts. Okay, if it just stops. And we looked at it with a pool ball as well. We looked at the numbers with it. So you can go back and look at this in the notes if you need to. But when something bounces, and you guys saw this with your RA too. If your cart bounced, you had the same problem. When it bounces, it means that you have a greater change in velocity. Okay, and that greater change in velocity is going to mean that you have a greater change in momentum or a greater impulse. Okay, and more force as a result, because it's going to be the force not just to stop it, but to make it go the other way. So that's why you don't want it to bounce, because it's more force. Again, if your cart bounced, you saw that. It's more change in velocity. That's why it ends up being more change in momentum, more impulse, and more force. So let's see. If they stuck together, on the other hand, it would be less. So the force of the collision would be less if they stuck together. It's more when they bounce. It's less when they stick. So number 11 should be C, and 60% of you got that one right. Again, if you need to go back and look at it again, it's in your notes. Go look at it again, or just make a note right now. Okay, if it bounces, that's more force. It's also more impulse because it's more force, assuming the time's the same, which it says here, assuming the time is the same.
So the collision would be less.
All right, number 12. Number 12 says, an 80-kilogram man runs into a brick wall at 12 meters per second, bringing him to a stop. If the collision time is 0.08 seconds, what magnitude of impulse does he experience? Again, we have a couple different equations for impulse. Depending on the information we have, we can use impulse equals force times time, or we can use impulse equals mass times change in velocity. Those are both valid equations for impulse. This one is the impulse equation. This is the change in momentum equation, but impulse is change in momentum, so they're both okay. When I read the question, I see that I have a mass, And I see that I have a change in velocity. He starts at 12 and he stops. So I have a change in velocity here of negative 12. I don't have a force, so I can't actually use this one because I don't know the force. I do know the time, but because I don't know the force, I can't use it. Could I find it? Sure. You have a mass, you have an acceleration effectively. So yeah, you could find it, but that's more work. So I would recommend using this equation instead because we don't know force. So instead we're going to use mass times change in velocity. Impulse equals the mass of the man is 80. His change in velocity is his final is 0. So 0 minus 12. Of course that's negative 12. So it's just 80 times negative 12. Which is negative 960. Now you'll notice there's not negative numbers here. But the question says magnitude of impulse. So they didn't even care about the sign. Okay, what magnitude of impulse? 960 newton seconds. Technically, the impulse is negative 960, but since it just asked for magnitude, we're just going to give the number value. The answer is D, and 78% of you guys got that one right. All right, number 13. Number 13, you guys did really well on number 13. 88% of you got it right. Okay, I will say this though, the wording on number 13 is a little bit confusing, and I meant to fix it. I actually changed this question a lot from last year and then forgot to change the wording in the answer choices. So I apologize, but that does mean that, and I'll explain it in a second, I actually took 2 different answers for this because of the confusion with the words forward and backward. Okay, but let's go ahead and solve it. Again, this one says a heavy cart carrying 2 masses collides with a light cart with only 1 mass in a physics lab as shown in the images below. Okay, so this is basically step 1, step 2, step 3. It's showing the parts of the collision. Here's before the collision, here's during the collision, here's after the collision. Okay, it says after the collision, the heavy cart moves leftward as shown in the bottom image. That's this one. What is the velocity of the lighter cart following the collision? Again, when you have a collision, we've said this a couple times, but the impulses are equal. Okay, they're equal in magnitude. Now, technically, they're in opposite directions, right? Because this cart's going to be pushed this way. This cart's going to be pushed this way. Okay, the forces are equal and opposite as well. So that they're going to be equal in magnitude, but keep that in mind. We're going to have to check our sign when we do the math. But our impulses are equal to each other. That means our change in momentum is equal to each other, and that's the equation we're going to do. Change in momentum of cart 1 equals the change in momentum of cart 2, or at least they're equal in magnitude. Okay, so if we look, we're going to take our mass of cart 1, which is 6, and cart 1 has a change in velocity. Its final velocity is negative 2.1 minus its initial velocity, which is positive 7.5. You do need to pay attention to your signs. When this one starts to go backwards, we're going to call that negative. We're going to call this positive. Okay, likewise, we're going to call this negative. So just keep that in mind. All right, so anyway, this is how you get the change in momentum of the first cart. And we're going to set it equal to the mass of the second cart is 4.3 times its change in velocity. I'll worry about that in a second. All right. So let's go ahead and subtract these. Negative 2.1 minus 7.5 is negative 9.6. And we're going to multiply that by 6, and we're going to set it equal to, at least equal in magnitude to this. Okay, now I already know that this one had an initial negative velocity, and this one's going to have a negative change that way. So again, they're equal in magnitude, but I am going to tack a negative sign onto one of them. It doesn't really matter which one. I just need to make sure that I set them opposite signs. Okay, so that's why I put a negative here. All right, so let's go ahead and see what 6 times negative 9.6 is. That is equal to negative 57.6. And negative 57.6 is equal to negative 4.3 times delta V. Again, they're equal in magnitude, but they are opposite in direction, so call one side negative. It doesn't matter. It's just to get the math right. All right, so negative 57.6 divided by negative 4.3. Those negative signs are going to go away. That's why it's important for us to do that. It would go away either way.
How did you know
And
it was negative?
again, they're in opposite directions. I already knew that they were opposite. One of them has to be negative. It doesn't matter which side you mark negative, they're going to cancel each other out regardless of which side you put it on.
Okay.
So this is going to be 13.395. I've rounded that a little bit, equals delta V. Okay, so that's what I got when I divided both sides by negative 4.3. So that's my change in velocity for this cart. So now let's go ahead and use that. 13.395 equals VF minus VI. VF is what I'm trying to find. I don't know its final velocity, but I do know its initial velocity is negative 8.7 because it's in the picture, and I'm subtracting negative 8.7. So that really means that I'm adding 8.7. So when I want to go to solve this, I'll subtract 8.7 from both sides. Let me get back to my calculator screen. And I have 13 point, I'll take the whole value. That whole number for this one minus 8.7. And you get this. Okay, and it is positive. It's going in this direction. Okay, now this is where it got kind of confusing because the words forward and backward are not really specific enough. The idea was to call anything this way forward, but relative to its initial direction, it is backwards from how it was going. So if you put backward, I gave you credit because I meant to put left and right. That's less confusing. Okay, but because of the wording, I actually took either B or C as correct because the wording is confusing.
Which question?
Okay, so the answer you should have put, what my intention was B, but like I said, I meant to I meant for this to say right and this to say left, and I forgot to change it. Okay, so if you put C, it still was counted correct.
So,
all right, so that's number 13. It should be 4.69 meters per second to the right would be a better way to write that. Okay, number 14. Number 14 was one that some of you guys struggled with. Again, only 55% of you got it right. It says a 1.75 times 10 to the third kilogram car traveling to the north is slowed down uniformly from an initial velocity of 35 meters per second by a 7,500 Newton braking force acting opposite the car's motion. What is the car's final velocity after 3.8 seconds? So, obviously this is going to be a calculation problem. It would be good to start by writing out our given information, starting with our mass, which I would prefer to write in standard form instead of leaving it as in scientific notation, but that's up to you. 1.75 times 10 to the third is simply 1,750. So I'd prefer to write it that way, but you don't have to. You can leave it in scientific notation if you want. It gives me an initial velocity of 35 meters per second to the north. I'm just going to call that positive 35 because I'm going to say that north is positive. And then I have a force of 7,500 newtons opposite. So that means it's south, it's negative. If you missed this problem, it's probably this sign that you forgot. Okay, so be careful with your signs. What is the car's final velocity after a time of 3.8 seconds? And we're looking for VF. Again, we can solve for VF using a kinematic equation because it's in 3 of those, but that would require us to know VI, T, A, and delta X, at least 3 of those things. And right now I only have 2 of them. So my kinematic equations aren't the best option, at least not immediately, although if you want, because you have force and mass, you could get acceleration and you could use a kinematic equation, and that's perfectly fine. Okay, however, what I do have the information for is my impulse momentum theorem equation. I have that. Okay, and so that's what I'm going to do so I can do it in 1 step. Now, again, if you did it the other way in 2 steps, you should be fine, but I'm going to use F times T equals M times VF minus VI. And then I can do it in 1 step. So my force is negative 7,500. We're going to multiply it by my time, which is 3.8. set it equal to my mass, which is 1750, times VF, which is what I'm looking for, minus VI, which is 35. So that's my substitution step. I'm going to go ahead and solve the left-hand side of this. Negative 7,500 times 3.8 is negative 28,500, and it's equal to 1750 times VF minus 35. From here, I'm going to divide both sides by 1750. If you want to distribute, you can do that instead, but I'm just going to go ahead and divide the 1750. Oops, typed it wrong. And I have this, negative 16.286 equals VF minus 35. Again, from here, if I want to solve for VF, I need to get it by itself. I'm going to add 35 to both sides. That'll cancel this and leave me with, I'm going to write it up here because well, I guess I can fit it, with VF equals, and it's positive now, 18.71 meters per second, and that is answer choice A for number 14. All right, like I said, 54% or 55% of you guys got this right. It's probably the sign. If you missed it, it's probably the fact that you forgot to put the negative sign on this. If you forget that, you will get the wrong answer. Okay. Let's look at the last one, number 15. Number 15 says, a baseball player with a mass of 94 kilograms slides for 2.47 seconds as he slides into home plate where he comes to rest. If the magnitude of the frictional force acting on the player is 740 newtons, how far does he slide? So this is a stopping distance question where they're asking us to solve for delta x. So I know I have to use a kinematic equation eventually. Okay, I'm going to have to. But let's go ahead and label what we have. We have a mass of 94 kilograms. We have a time of 2.47 seconds. We have a final velocity of 0 because he says he comes to rest. We have friction. I'm going to go ahead and call my friction negative because it tells me the magnitude, and I'm going to assume that he's moving in the positive direction. So I'm going to call my friction negative 740 newtons. And I think that's all I have. Yeah. So with this information, if I want to find delta x, okay, I've got a few equations. I have this one, delta x equals VIT plus 1/2 AT squared. I have delta x equals VI plus VF divided by 2 times time, and I have VF squared equals VI squared plus 2A delta x. Those are the three equations that have delta x in them. All of these equations require us to have VI. I can't do anything without VI, so I need to solve for my initial velocity. And I can do that because I have MT, VF, and F, and I can use this equation that I used just a minute ago. F times T equals M times delta V, keeping in mind that delta V is VF minus VI. So I'm going to solve for VI before I do anything first because there's no way for me to get delta X without having VI. It's in all of them. So let's do that. I might also want A, but I do have an option without A, but I don't have an option without VI. All right, so my force is negative 740. My time is 2.47. My mass is 94. VF is 0, and we're looking for VI. That's my substitution step. So let's go ahead and solve the left-hand side. Negative 740 times 2.47 is negative 1,827.8. And that is equal to 94 times negative VI. I'm not going to write the 0 again. It's just negative VI. Divide both sides by 94. and you get negative 19.44 equals negative VI, which of course means that positive VI is positive 19.44. All right, so I have my initial velocity. So can I find delta x? Let's see. If I have VI, this is the only one that doesn't have A in it, so let's check that one. I have VI, I have VF, I have T. Yeah, I can use that equation right there. Your other option would be to use F equals ma, get your acceleration, and then you can use any of the three. Okay, but I can actually use this one without even finding acceleration. So that's what we're going to do. Delta x equals VI is 19.44 plus VF, which is 0, divided by 2 times my time, which is 2.47. All right, so 19.44 divided by 2, because plus 0 I don't have to worry about, and then times 2.47 is 24.01, which is answer choice D. So the answer you should have selected for number 15 is D, and 2/3 of you guys got that right, 67%.
So D? Okay.
D. All right, so again, on your test tomorrow, you're going to have similar problems to these in the multiple choice section, and then of course you also have free response. If you didn't do so hot on this quiz, please do the unit summary, because the unit summary is going to not only be a redo, because if you failed it can bring your grade up to a 70, but it is also a great review for your test. So please work on that unit summary for extra practice. In fact, you could even use your time right now in class to do that, but you guys have a test tomorrow, so I want you to make sure you're reviewing before that.